Yes, we know that beryllium's ionization energy is greater than borons, right? And just below the beryllium, we have magnesium, and below boron, we have, right? So, in that sense, even magnesium's ionization energy should be greater than aluminum. We have to apply the same reason, right? So, why is that? We know that in case of magnesium or beryllium, the electrons are in S2, right? So, if you write the electronic configuration of magnesium, S2, S2, 2 plus 6, 3, S2. And if you write the electronic configuration of aluminium, it is 2s2, 2 plus 6, 3s2, 3p1, right? 3s2, 3p1. So if you observe here, the atomic orbital is completely filled and electrons are filled in s orbital. Here, the electrons are not completely filled or even half filled. Here we have only one electron in the p orbitals. So compared to this, removal of electron in this 3p orbital is pretty easy. So that's why the ionization energy is also less. In another sense, we can also tell that here the electrons are in s orbitals, which is more penetrating than the p orbital. That means this is more close to our nucleus and it is more difficult to remove the electron from this s orbital than the p orbitals, which is a bit finer. Right? So if you observe the options, atomic size is not relevant over here. The only relevance is aluminum has one electron in p orbital, so we can take this. Okay, yes. So next question, consider the following statements. The discovery of inert gases later on did not disturb Mendeleev's arrangement. I don't think so, right? So, I mean, this is right statement. So if you observe the Mendeleev's periodic table, the noble gas, yes, given place for the noble gases also in this periodic table. So that doesn't make any sense, that statement. So coming to next statement, in the present periodic table, the periodicity in the properties of elements is related to the periodicity in their electronic configuration. Yes, this is also true, right? The periodic table is based on the atomic number, right? And we write electronic configuration and we divide the period table into different blocks based on the same electronic configuration, and these different blocks show periodicity in properties, right? And they have similar behavior, those block elements and all, right? So we can say that both of these statements are true. So the question is, which of these statements are correct? We can say first and two both are correct, so it's option C. Okay, coming to 17th question. Sodium sulfate is soluble in water, whereas barium sulfate is sparingly soluble. Okay, whenever you get this kind of question, look for the option where they have given reason for barium sulfate. So if you observe, in B, they have given reason for barium sulfate, and in A and D, no. What actually happens when you take alkaline earth metal, right? Barium is alkaline earth metal, right? So when you take alkaline earth metal and when you take sulfates, for example, if you take beryllium, magnesium, calcium, strontium, barium, right? And sulfates, they are sulfates, same thing. So the anion is same. We're only changing the cation. The anion size is same, and only the difference we can observe is in the change in the size of the cation. So if you consider the lattice energy, there is no much difference that you could observe in the lattice energy for all these compounds, because lattice energy, we know that it depends upon the charge and it is inversely proportional to the radius of cations and anions. So if that is R A plus RB, right? Radius of cation and anion. So if one of the radius is constant, that is sulfates, anion's radius is constant, only the cationic radius is differing by slightest amount, the lattice energy change would not be much. So that's why we don't consider lattice energy changes in this case. We can only observe the changes in the hydration energy. And we know that when we move down the group, what happens? The size increases. As the size of these cations increases, the hydration energy decreases, right? As the size increases, the hydration energy decreases. They are inversely proportional to each other. So, if you move till barium, the size is very big, the hydration energy is very small. So, that's why it cannot be soluble in the water, right? So, if you observe the option B, the lattice energy of barium sulfate is more than its hydration energy. What does that mean? The hydration energy is very small when compared to your lattice energy, which is very high. If you're not being able to break the lattice and if you're not being able to dissolve that barium ions in a solution very well because it has very less hydration energy, it is not soluble, right? So the option should be B. Your answer should be option B. Okay. Coming to question number 18. Which of the following is the reason for the different chemical behavior for the first member of a group of the elements in S and P block? So this is nothing but your anomalous properties. They're asking the reason for your anomalous properties. And we know that the reason for the anomalous properties is small size, large charge to radius ratio, and also high electronegativity. But in this question, they have given low electronegativity. This should not be the option. So 1 and 2 is correct. That could be the reason, but 3 is not the reason. So we can take option C as our answer, right? 1 and 2. Okay, coming to question number 19. An atom has electronic configuration this. You will place it in which group? This is very easy question. If you observe the electronic configuration, you can observe one thing, that the electrons are being filled in D subshell. That means it should be a D block element. And how is it? 4s2 3d3. How do you start the D block elements? 4s2 3d1, 4s2 3d2, 4s2 3d3, right? Scandium, titanium, vanadium, right? So where does the transition metal start from? From which group? From third to 12, we have transition metals. So this is third, this is fourth, then this would be fifth group, right? So the option A should be the answer. Yes, 20th question. An element X occurs in short period having electronic configuration Ns2Np1. The formula and nature of its oxide is Ns2Np1 is general electronic configuration of 13th group elements, your boron, aluminium, right? Gallium, indium, thallium. And we know that if you remember, aluminium oxides are amphoteric in nature, right? Amphoteric oxide, it forms amphoteric oxide, Al2O3. So it should be option C. Okay, 21st question. The electronic configuration of metal is this 1s to 2s to 2p6, 3s1. The formula of its oxide will be, okay, which is this metal? If you observe the electronic configuration, the atomic number is 11. So the metal is sodium. So forms, sodium can form this monoxide. It can also form, what do we call, peroxide. So it is more stable with this superoxide or peroxide. So it is. If you observe sodium metal ಹೇಗಿರುತ್ತೆ? Na2O, sodium oxide, Na2O. Or if you take alkali metals other than like this, Li2O, right? In this form. But generally speaking, sodium can also form peroxide, Na2O. Okay, the higher alkali metals will form superoxide like KO2, RbO2, etc. But since the electronic configuration over here is given this, SO3, no. MO, no. It cannot form NaO, no. It can only form Na2O. Or if they had given this option, it would be more precise. Na2O, it can also form peroxide. Okay, so option B should be your answer. Okay, hybridization of the underlying atom changes in. Okay, so here they've not underlined any atom, and we should consider this central atom, our nitrogen, aluminium, and oxygen over here. Right? So if you observe B and C, here there will be no change in the hybridization. What is happening? Here actually, if you take H2O, here hybridization is sp3. This oxygen will donate electrons to the H plus. It's kind of coordinate bond that is being formed. So there will be no change in the hybridization in this case. sp3 hybridization remains as it is. Even if you take ammonia, ammonia has one lone pair electron. So if there is any H plus, it can donate electron to this and it can form NH4 plus. So here ammonia is in sp3 hybridization state, and here also nitrogen is in sp3. So there is no change in the hybridization in all these cases. Only thing is A, where we can observe the change in hybridization. If you take this, what is this? Aluminium hydride, right? AlH3. If you use this formula, number of valence electron in aluminium is 3 plus single bond 3 divided by 2. 6 by 2 is equal to 3. So it should be sp2 hybridized, isn't it? Now, if you observe this, 3 valence electron plus 4 plus 1. So what has happened? It is 8. 8 by 2, 4. That means it is sp3 hybridized now. Okay, here you can observe aluminum hydride is changing from sp2 to sp3. So the hybridization only changes in A, okay, not in the B and C. Here the hybridization remains in. Okay, coming to question number 23. In phosphate ion, they have given the formal charge on each oxygen atom is. So if you write the phosphate ion, it's like this, right? PO3, PO4, 3 minus, right? Now, how do you calculate the formal charge? So you try adding all this charge, -1, -1, -1, and here the charge is 0 on this oxygen atom, divided by number of oxygen atom. How many oxygen atom do we have? We have 4. So this is -3 by 4. -3 by 4 is minus 0.75. This is minus 0.75. Right? This should be your formal charge. Now coming to resonating structure, sorry, bond order. So in order to calculate bond order, you have to observe the number of resonating structure. So now we can have 4 resonating structure for this, right? So this can come, this can go. So you can have PO minus, O minus, double bond, and again. So you should write the resonating structure in a straight line. Since I have no space, I'm writing like this. So it is PO minus, minus, double bond O, and O minus. So you can also write another resonating structure. So basically, the number of oxygen atom you have will give you the number of resonating structure. So, right. So now we can observe that we have 4 resonating structure. 1, 2, 3, and 4. So we have 4 resonating structure. And how many bonds do we have? 1, 2, 3, 4, 5. So if you have to calculate bond order, you have to take number of bonds, total number of bonds in the structure and total number of resonating structure. We have 4 resonating structure and we have 1, 2, 3, 4, 5. 5 bond. So 5 divided by 4 will yield to 1 bond. So it should be option C. Okay. Yes. 24th question. An ether is more volatile than an alcohol, having the same molecular formula. This is due to they have given ether, which is ROR, an alkyl or aryl group attached to an oxygen atom. And they have also given alcohol, which is ROH, right? So they're asking about the volatility. Volatility means which one would be easily vaporized when you boil it, which whose in other terms you can also think of the compound having less boiling point or which could be evaporated very easily. This depends upon the intermolecular attraction, intermolecular forces. Okay. So in ether, you can only have weak dipole dipole interaction, right? Oxygen will be more electronegative than alkyl group O minus R plus. So in the same way, there will be more number of such molecule, right? So this negative could be attracted to this positive alkyl group, right? Same, this negative can be attracted to another positive alkyl group. So this kind of dipole-dipole interaction we can observe in this ether, weak dipole-dipole. But if you consider alcohol, here we can observe hydrogen bonding, right? Hydrogen is covalently bonded to electronegative oxygen atom. Now we have one condition, right? In hydrogen bonding, the hydrogen should be covalently bonded to electronegative atom. So the condition is satisfied. Now we can observe intermolecular hydrogen bonding, right? Partial negative, partial positive, again partial negative, partial positive. Now this, there will be an electrostatic attraction between these two, isn't it? Positive, negative, negative, positive. So we also know that hydrogen bonding is the strongest intermolecular forces among all the other forces. So if alcohol have hydrogen bonding as its intermolecular attraction, it is very difficult to break these intermolecular attraction, right? If it is difficult to break this intermolecular attraction, then obviously the boiling point would be high. That means it is not easily volatile. It is less volatile, right? So in ether, compared to alcohol, there is weak intermolecular force of attraction. We have weak dipole-dipole. This could be broken easily when compared to this hydrogen bonding. So this ether would be more volatile. Okay. Now in the option they are asking you reason. So if you observe intermolecular hydrogen bonding in alcohol is the answer. An ether is more volatile than an alcohol having the same molecular formula because in ether we don't observe hydrogen bonding, but in alcohols we observe hydrogen bonding. That's why alcohol is less volatile and ether is more volatile. Okay, 25th question. The maximum number of 90-degree angles between bond pair and bond pair of electrons is observed in. Okay, they have given you different hybridization, isn't it? So this is a very direct question. And we know that in sp3d2 hybridization, all the bond pairs are 90-degree to each other, right? All the bond pairs are 90-degree to each other. So we have 6 bond pairs. So we have 6 90-degree angles between two bond pairs. So here we can observe 6. If you consider sp3d, we have 2 bonds which are 90 degree, right? So we can say This is 90 degree to this is 90 degree to this, 90 degrees. So maximum number of 90-degree angles we can only observe in sp3d2. Okay, here we in sp3d we have only two bonds which are at 90 degree, but here all the bonds are 90 degree to each other in case of sp3d2. Yes. 26th question. Which of the following is the correct increasing order of lone pair of electrons on the central atom? So you have to apply this formula and try writing the structure. IF7, so it is 7 valence electron plus 7 bond pairs, single bonds, monovalent atoms. So it is 14 by 2, that means 7. So 7 means it will be having this structure. It is pentagonal bipyramidal. So do you have any lone pair? No, we don't have any lone pair. All the pairs are bond pairs. Even if you try 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 6, 7. So it is completely bonded. You don't have any lone pair. Here, 0 lone pair. In case of IF5, so what is it? 7 plus number of monovalent atom? 5 by 2. 12 by 2, that means 6. So it is sp3d2 octahedral. So it should be like this. IF5, right? Octahedral. 1, 2, 3, 4, 5. So that means 5 valence electron it has used. How many number of valence electron we have in iodine? 7. So another 2 electron is acting as lone pair. So we have 1 lone pair in IF5. So in ClF3, if you take ClF3, so number of valence electron is 7 plus 3, 10 by 2 is equal to 5. So it is sp3d trigonal bipyramidal structure. We'll write ClF3. If you remember, we will be writing T-shaped molecule, right? 1, 2, 3. 3 valence electron, done. So another is 4, 5. 6, 7. We'll be keeping lone pair at this position at equatorial because it will minimize the lone pair bond pair repulsion or lone pair repulsion as well. So how many lone pair we have? We have 2 lone pair. Yes. What about XCF2? If you take XCF2, the number of valence electron is 8 plus monovalent atoms of single bond is 2 divided by 2. 10 by 2 is 5. Again, the same trigonal bipyramidal structure. So if you write XEF2, 1, 2, 3, 4, 5, 6, 7, 8. Total we will be having 8 lone pair on 8 valence electron in xenon. So 2 is used in bonding and the others are acting as lone pair. So we have 3 lone pair. So number of lone pair order should be your A. Okay. So coming to 27th question. Bond order normally gives idea of stability of molecular species. All the molecules, that is hydrogen, lithium, and this should be boron. boron molecule have the same bond order, yet they are not equally stable. Their stability order is right. We always calculate stability of any molecules, or we think of stability based on the bond order. Right now, if you observe hydrogen, boron, and lithium molecules, the bond order is same for all the molecules. Now, how to determine the relative stability? So here we'll take help of the MOT again. So if you try writing the energy level diagram, in hydrogen molecule, hydrogen will be having 1s1. So this is 1s, sigma 1s. So it will be sigma 1s, and here sigma star 1s. Right. So how many electrons do we have? We have 2 electrons, 1, 2. Right. So 2 electrons are in the molecular orbital, that is sigma 1s molecular orbitals, and we don't have any electrons in the anti-bonding molecular orbital. So ABMO electrons is 0, right here, 0. Now if you observe lithium molecules, what happens in lithium? Lithium, if you just, I'll just write hydrogen's ABMO electron, I mean anti-bonding electrons, that is 2 hydrogen. So if you take lithium, what will do? So lithium is 1s2, 2s1, right? So if you take lithium, 1s2, 2s1. So that means 1s2, this is 2 lithium atom having 2 electrons in its 1s orbitals. So totally we have 4 electrons. Those 4 electrons we have to fill in the molecular orbitals 1, 2, 3, 4. Right? So this is filled. Next is your 2s orbital. So we have only 1 electron in 2s orbital. So if you write that, so 1, 1. In this 2s 1 and another lithium atoms 2s 1. So this is sigma star, sigma 2s and sigma star 2s. Totally we have 2 electrons, 1, 2. Right. So if you observe in lithium molecules, we have 4 electrons in bonding and 2 electrons in anti-bonding. So in hydrogen, okay, hydrogen it was 0, right? There was no anti-bonding electron. But in lithium we have 1, 2. Sorry, 1, 2, 1, 2 bonding electrons. So what about boron now? So boron's electronic configuration is 1s2, 2s2, 2p1. So we'll keep this as it is. Just add 1 more electron in 2s orbital and 1 more electron in this 2s orbital. So 1, 2, 3, 4, 1, 2, 3, 4. Now again the electrons are in 2p orbitals. We'll try to fill electrons in p molecular orbitals, pi molecular orbitals and all. So this is 2p. Again, this is another 2p. Okay, so we have 1 electron. So if you write the energy level diagram, it should be right. So here 1, 2. Right, 1 and 2. Right. So now if you observe, how many electrons do you have in antibonding orbitals of boron? 1, 2, 3, 4. We have 4 electrons in antibonding. Always remember, more the number of electrons in antibonding orbitals, lesser will be its stability. Okay, so here stability of hydrogen will be more than lithium than boron, because in hydrogen we don't have any electrons in the antibonding orbital. So it should be option D. Okay, coming to 28th question. In the anion CHOO minus, how is this CHOO minus? The 2 carbon oxygen bonds are found to be of equal length. What is the reason for it? Whenever you observe an equal bond length, the only reason should be its resonating structure. H3O minus is like this. Okay. In this is formate ion, and here we will observe the resonance. The electrons over will be delocalized. We can write the resonating structure for this. H3O minus. So here, due to the resonance, the bond characteristics are averaged, right? Always the bond characteristics are averaged. So that's why both of these carbon-oxygen bond length would be equal, right? They're neither single or double bond. They're kind of intermediate and they're kind of equal. Okay. So the reason for this is delocalization of this electron, and the concept is called resonate. It has two resonating structures. So we can say option C should be our answer. Okay. 29th question. The molecules BF3 and NF3 are both covalent compounds, but BF3 is non-polar, whereas NF3 is polar. Always remember, the polarity depends upon the dipole moment. Okay, whenever you're given polarity kind of question, it depends upon the dipole moment. So we know that BF3 is a planar molecule, right? You observe the structure of BF3, it is planar. So the individual bond dipole is like this towards more electronegative fluorine atom, right? Directed towards fluorine atom. These two bond dipole will have resulted in this direction, and this will be in this direction. So now these two will cancel out each other. Okay, when these two dipole moment cancel out each other, that is dipole moment is equal to 0, the polarity will be this. That means there will be no polarity. So we can say that this molecule is non-polar because this has zero dipole moment. But in case of NF3, we will observe dipole moment, right? So NF3 molecule will be like this. Bond dipole towards the fluorine atoms, and you will have another lone pair electron which will be having dipole. So here, although these three dipoles are directed towards this direction, although we'll observe some of the dipole moments being cancelled out, but not completely. We'll observe some amount of some magnitude of dipole moment in NF3 molecule, but in case of BF3, dipole moment is zero. So that's why here this molecule can be considered as polar, but BF3 is not polar. So it should be D. Right? BF3 is planar and NF3 is pyramidal, right? This shape is pyramidal. NF3, NH3, those shapes are pyramidal in shape. Yes. Among lithium chloride, rubidium chloride, beryllium, and magnesium chloride, the compounds with the greatest and the least ionic character respectively are, right? This is based on polarization concept. So if you just calculate the covalent character, we'll get to know about the ionic character, right? So in case of beryllium and magnesium, the ions are 2 plus ions. Lithium and rubidium are plus 1 ions. So we know that covalent character is directly proportional to polarizing power of cation, which is inversely proportional to size of cation, and which is directly proportional to charge of cation, right? As the cation charge increases, we can see covalent character increases. So here the charge of this beryllium and magnesium is higher than the lithium rubidium. So here we can observe the covalent character. And between beryllium and magnesium, which one will be having more covalent character? So here we can observe the difference in the size. Here the size of beryllium 2 plus is very less, right? Because on moving down the group, the size increases. So as the size of beryllium 2 plus is less, size decreases, covalent character increases. So we can say beryllium chloride is having high covalent character. So that means it will be having least ionic character. So least ionic character should be your beryllium. Okay. So now if you observe the option, we have two B and C having least ionic character. Now between lithium and rubidium, if you observe, obviously they will be having more ionic character than beryllium and magnesium. And between lithium and rubidium, what do we say? Rubidium having greater size, lithium having least size. Lithium having least size can have covalent character, more covalent character. But rubidium having greater size can have least covalent character, but will have more ionic character. So it should be option B. Okay, option B. So this is the solutions for chemical bonding and periodicity. I hope you people understood this. Thank you.